Hi again. Let's discuss the concept of torque. Why do we define torque? Why do we need to define torque? Now, the concept of torque is related to the rotational effect of forces. The fact that forces, when applied on an object, forces can rotate objects, right? So let's say you have the same, let's say I'm applying equal and opposite, equal forces, right, in the same direction on this object. So this force is moving the object, these two forces, right, in a straight line. This is linear motion, right? But now the same two forces applied over here. So this is, let's say this is 1 Newton, this is 1 Newton as an example, right? So I'm applying a 2 Newton force, right? Now if I keep the forces the same, okay, and apply them over here, right? Now you know that this is now negative 1 Newton and this is positive 1 Newton, right? So the net force on the object is 0, right? But interestingly, if you apply the forces rotate the object, right? And the rotation will go faster and faster if the forces are constantly applied to the object. So in this case, even though the net force is 0, the object is being rotated by these forces, and the rotation will go faster and faster, right? So these forces are producing a large rotational effect. Okay, we need to take that into account. We need to take into account the fact that forces can rotate objects, and rotation always takes place around some point, right, which we call the pivot point. So let's now fix this point as our pivot point. Okay. Now let's say I apply a force over here, right? So let's see what that rotational effect depends on. So if I apply a force over here, it rotates. If I increase the force, then of course the rotational effect gets larger, right? So it obviously depends on the magnitude of the force. Now you can also see that if I'm going to fix my force, okay, let's say 1 Newton, I'm fixing it, and I'm going to change the angle. The rotational effect of the force is actually decreasing as I'm decreasing this angle and making it along the axis, right? So it depends on this angle. My force goes like this. So it depends on this angle that the force is making with this line, which we call the radial line, that connects with the pivot point to the point at which I'm applying the force. I'll draw all these forces. I'll draw these forces and the radial lines in a minute. So we saw that if I increase the magnitude, the rotational effect increases. If I fix the magnitude and change the angle, the rotational effect changes based on the angle. So it's maximum at this angle, which is of course 90 degrees with this line, and decreases as the angle becomes 0, right? So it's something like sine theta, right, that you feel is over there because it's maximum at 90 degrees if you choose this angle, and minimum at 0 degrees. And it also depends on one more thing. So you can see that if I apply this is my pivot point. If I apply the force, the same force on the pivot point produces 0 rotational effect. And if I keep the force fixed and I go away from the pivot point, the rotational effect of the force is increasing. Okay. It actually also depends on the distance at which I'm applying the torque. That's why when you open the doorknobs are always at the farthest end from the hinge, right? Because you want to apply the maximum torque to open the door, right? So you want if the door hinge was over here, you have to apply a really large force to open the door, right? So in order to increase the rotational effect of your force, you apply the doorknobs are over here, so it's easier to open the doors or to close the doors. And you always apply a force perpendicular. You always go perpendicular. You never go like this, right? In normal situations, you never go like this or this, right? You always open the door perpendicular, or open or close the door perpendicular to the door. Okay, so that's what torque is, right? It is the rotational effect of the force, and it depends on the magnitude of the force, the angle, and the distance from the pivot point. So let's write that in the form of an equation. The magnitude of torque is equal to R times F times sine theta. Okay. And let's assume again that same object, right? This is the object, Okay, and this is the force I'm applying, right? I applied, force using my hand. This is that force, and this is that angle theta. So this is that radial line. This distance is r, okay, and this is the pivot point. Usually, sometimes written as O or P, same thing. So it depends on all these things: where the pivot point, the distance of the pivot point to the line, to the point at which the force is being applied, and the angle that the force makes with the radial line. Okay, this theta is this angle. Okay. Now there are two methods to calculate the torque, right? So we saw that we need this component of the force, this perpendicular component of the force, because as we saw that if you apply a force that goes along the line of action of the force goes through the pivot point, right? Now the line of action of this force is going through the pivot point, and this also, right? All these forces are producing zero torque, right? Because you can say, of course, that the angle is 0 or 180 degrees, or you can say also that r is 0, because you can extend the line of action that goes through the pivot point. So any force or its component that goes through the pivot point produces zero torque. So we want this component, which is, of course, as you can see, if you draw the triangle, it's f sine theta. So this is that perpendicular component of the force, and you can also write this as r times f perpendicular. So that's so once you have a situation where you have to calculate the torque, you can find this perpendicular component multiplied with this distance. You can get the magnitude of the torque, and so you can call this method 1. Okay. And just before moving forward, a convention is that counterclockwise torques are positive and clockwise torques are negative. So this force is trying to rotate this object around this pivot point in the counterclockwise direction, so it produces a positive torque. If it was in this direction, it will produce a negative torque. Okay. So this is method 1 to calculate torque. Another method, which is very useful, as we will solve a problem, you'll see it's very useful, is, let's draw the same picture. Okay, so here's again your pivot point, and let's draw the same force. And this distance is r. Okay. Now what I'm going to do in this method is I'm going to extend the line of action of the force. I'm going to extend this line, okay? And I want to draw perpendicular from this line to the pivot point, okay? So I want to draw a perpendicular because I want to make this a right triangle, okay? So this is 90 degrees. Now we saw that this angle, this is theta, so this is going to be theta as well from geometry. So this is called the moment arm of the force. This is r perpendicular, and you can see that this is a right triangle. It is the opposite side, so r perpendicular is r sine theta. So you can write the same. You can write the torque as tau equals r perpendicular times f also, which is the same thing. It will give you the same answer, but when we solve problems, you'll see that this method, the method 2, is much easier than method 1. This method 1 where you find the perpendicular component of the force. Okay. So these are the two methods. If you have any question, post them in the comments. We will next do an example on related to torque, where we will demonstrate that this method is very useful. Okay, thank you for watching.